I'm Ivan Cukic, or how most of you pronounce me, Cukic. So just call me Ivan. I'm a KD developer. I've been a KD developer for a decade now. So this is the reason why I'm wearing a KD t-shirt. I've been working around functional programming for quite some time. I'm now finishing a book on functional programming in C++. And I've been a regular visitor of the stage on Meeting C++. So usually I start all of my presentations with a couple of disclaimers. The only disclaimer that survived all the years that I've been teaching is a quote by Phil Wadler. The idea is that you should always write your code in a way that your future coworkers will not have the desire to kill you. So Phil Wadler is one of the really smartest people that I've ever seen, so you should probably obey his ideas really in detail. Now you might have noticed that the title of the talk is a little bit different to what you have in the schedule. So there are a couple of reasons why I decided to add a few stuff, and we're going to have tomorrow a talk by Juan Pedro about, he's the author of one of the greatest libraries for functional data structures. So I decided to put less emphasis on the functional data structures because you'll be able to talk with a guy who actually is doing a really neat library. But we'll probably cover them at some point today. So functional programming is not really a thing. It's just a collection of different ideas and idioms. And just like all other idioms, it's meant to make your code safer. One of the problems that we tend to have in C++ is when we write our programs, we can sometimes make really huge bugs by allowing our programs to have invalid states. So one of the things that we should always strive to do is to make invalid states impossible for our programs to ever be in. The second thing is when we are in the concurrent environment, we tend to abuse those states. So we need to pay attention when one concurrent process can change the state and when the other can and stuff. And functional programming provides us with idioms that are highly applicable even in object-oriented world for both of these things. The first part of the talk will be about how to make your states valid. And the second part will be about functional data structures, or the data structures that allow you to work in a concurrent environment without any need for locking and similar stuff. So imagine we want to implement a simple program which connects to a web server, for example, isocpp.org, and counts the number of words in the web page. We have three different states. The initial state, we haven't yet started counting. We just know which page we want to fetch. The second state is, okay, we opened a socket, we are communicating with the server, and we are fetching the data and counting. And the last state is, okay, we finished counting, so we have the result. Usually, in object-oriented world, we would create a class which is able to store all of these states. So for example, our structure, program T or state T, would have two Boolean flags, whether it has started, whether it has finished, then an unsigned count, a string representing the URL, and a socket to the web page. The problem with this structure is that unsigned count equals 0. It's actually not needed until we start counting. So it doesn't need to even exist in the initial state when we haven't even established a connection to the web server. The URL is not needed after we connect to the server. If we have connected, then we don't care whether it's isocpp.org or something else, we have a socket. So we don't need to save this string while we are counting the words. And the socket is only needed while we are counting. So as soon as we finish counting, the socket should go away. If we implement it like this, it will not go away unless we actually explicitly close it. And this is the usual approach that we always take when implementing C++ object-oriented, not only C++, but most of the object-oriented applications are done in this way. Now, obviously, we wouldn't have two Boolean flags, we would have an enum. But the point of two Boolean flags is just to overemphasize the problem of just throwing everything in a class. So one of the possible states that our class could be in is that started is false, finished is true, and count is 42, although we haven't counted anything. And this is something that tends to lead to a lot of bugs. A couple of months ago, I was in Akademgorodok in Siberia, and they have a really neat monument to all the mice that were used during the DNA experiments. And it got me thinking about the DNA itself. So what is a DNA? DNA is a class where we put a lot of variables. Each of those can have 4 different values. So instead of actually saying, okay, this is a human, this is a dog, you would have a huge array of values where each of the values can have exactly 4 different states. Now imagine how many valid DNA chains are there in the world. There are exponentially a lot of different DNA chains, but just a few of them are actually valid, and you can get a real life out of it. So the DNA is the biggest object that I've ever seen in the world, and the one with the biggest amount of bugs. Just imagine you lived near Chernobyl, and just a few items in your DNA chain changed. You could have 3 eyes, 6 fingers, or most likely you wouldn't even be born. So bugs in biology are really cruel, but they're not any less cruel in programming world. Just imagine implementing your software like a DNA and your airline developer. Just have a plane, suddenly decide, okay, it's now completely okay for me to switch the engines off and go dive down. Because there was a state and somebody changed the state. And it's invalid state, but who cares? So instead of doing what is called product type, which is if you have 2 types, a product is a type that contains both of them, we can try to constrain our types but by using something else. Okay, let's skip a couple of slides. We can use sum types. So instead of having types A and B and producing a type which contains both, we can create a type that just contains a single A or a single B, but never both at the same time. So in terms of mathematics and set theory, it's a union of 2 types. And that's why it's called a union type or a sum type. Now, in C and C++, we have had unions for a long time. Usually the C union, which is completely unsafe and everything else. But if we wanted to implement our current program, we could maybe start with an enum. What is an enum? Enum is a sum of 3 values, this particular one. So it's a sum type, but a really simple sum type. It can't really contain sockets or anything else. One approach that was really common during past ages in C++ is to implement sum types through inheritance. So instead, if you want to have a couple of different states, you will create a superclass called, for example, a state T, and then you would inherit all of those specific states in your class from that superclass. So for example, the class is state T. In order to have it more efficient, we don't want to use dynamic polymorphism and dynamic dispatch. We are going to use tags. So we will have, for each of the substates, we'll have a unique identifier, an integer. And then we will be able to just tell exactly which state we currently possess. So if we wanted to implement the initial state, as we said, just contains a string URL. It doesn't need to contain the count. It doesn't need to contain the socket. So we would just create init t state, which inherits from the main state, and it has the ID 0. So we have a lot of boilerplate to create for this simple class. Instead of just being able to say, okay, we just want a string, we have to create an enum or a ID for our class, and we need to create a constructor which initializes that ID. For the running state, it's similar. The ID will be 1. Again, we need a constructor and we need a couple of items inside. So we will have the unsigned count, because this state is meant to count the words. So we need the number of words we already counted, and we need the socket, because we are reading the words through the socket. And the last state doesn't need to contain an URL, it doesn't need a socket, it just needs to contain a const count. Now in this case, since this is a final state, we stopped counting, we can even declare the variable to be const. And we have 3 different states. If we want to create our program, we can just say, okay, our program is a unique pointer to state t. In different periods of time, that pointer will be a pointer to init t, or to running t, or to finish t. So we have created a union type. It can't be more than one state at the same time. So it can't be both init t and finished t. Okay? And for example, the function that processes when the counting is finished would look something like this. We would assert that if counting finished has been called, it means that we were previously in the counting state. So we are asserting on that, and we can rest sure that in production, this will always be the case, because we shouldn't ever call counting finished on any other state apart from running. So when we finish the assert, we just do the static cast. We have the instance to the running t state, and we can then use it. Because now we have finished, we can just reset. The pointer should no longer point to the running state, it should point to the finished state. What will happen? The previous state will be destructed, which means that the socket will automatically be closed, and all the resources you acquired for that particular state will be freed. Which is something that if we obeyed the initial object-oriented idea, we would have to close all the items manually. So this is one huge win. Okay, we can skip. So if we use the inheritance-based sum types, we won't be able to have any invalid states unless you count a null unique pointer, but that you wouldn't ever do. The cool thing is that if you want to extend it, if you want to allow, for example, plugins, dynamically loaded plugins to extend your state space, you can easily do it. The plugins would just inherit from the supertype state t. Again, we have the automatic resource disposal. If one state is finished and you switch to another, all the resources that were used in the previous state just are freed. The bad part about inheritance, first, it's a lot of boilerplate. So we need to create tags, the IDs, and everything else. And the second part is that inheritance, you're going always through a pointer. And if you have a collection of things, it can slow your program down. So this is not the perfect choices in most of the situations. You should use the inheritance-based sum types only if you want dynamically to extend the set of states, or if you actually really need the object-oriented inheritance hierarchy. Instead, you should use a proper type-safe union. Okay? So what is a type-safe union? Instead of having a pointer to an instance of something, you just have a structure which is able to hold an instance of init, an instance of running, or an instance of finished t. And it will hold it in place. It will not allocate it on the free store or anything else. The structure will have the size of the largest state that it wants to be able to store. And depending on the time, it will store one of these inside it. Now, this was possible to implement in the old days using the C union. And then you would have a tagged union. Again, implement ID is a lot of boilerplate. Fortunately, we got a really, really useful class called, template class called std_variant, which does exactly this. A variant creates a new structure, which is able to contain, in this case, exactly one init t, or exactly one running t, or exactly one finished t. And to repeat, it will contain it inside of the variant itself. It's not a pointer to anything. So you don't have to go through pointers. You don't have all that performance degradation that you would have with the inheritance-based sum types. And you don't have the boilerplate, at least not in this part of the program. So when you create a structure, init t, you can just put string URL inside. You don't need to pay attention to its ID or anything else. You don't need to inherit from a super type. So init t, running t, and finish t are completely separate structures. But you're creating a variant that is able to hold any of those. Is everything so far clear? So how would you use std_variant? One of the functions that exists is the getif. Now, the getif function is a little bit strange. It doesn't really get a variant. It gets a pointer to a variant. So it allows you to pass a null to getif. In that case, it returns a null. If you pass a valid variant object, then it will check, okay, is this instance of the variant containing an instance of running t? If it contains running t, you'll get a pointer to the state. And if it contains anything but running t, you'll get a null. So if you want to use the getif, you would use it like this and then assert, okay, state should never be a null pointer. Because like in the previous example, if somebody called counting finished, this means that the previous state must have been running. And then, in order to switch states, you just need to say, okay, mState equals what is the new state. The new state is finished, and we pass the count, how many words we counted so far. Is this okay? Alternative to getif, you also have std::get, which will, if I remember correctly, throw an exception if you're trying to get something that is not currently in the std_variant, but you usually don't want to use it. I think getif, if you're an imperative programmer, getif should get you everywhere. Still, we can have no invalid states, not even the null pointer. std_variant can have some special state which you can achieve through a lot of exceptions and bugs in your code. But if you don't really try hard, then std_variant will always contain exactly what you expect it to. The set of states is not open, unlike the inheritance-based. So if you want to add new states, you'll actually have to change the actual type. You'll have to say std_variant of and then a list of types. So this means that you shouldn't probably use std_variant inside of the API, because if you want to change it, you're probably going to destroy the binary compatibility. If you add a new state which is larger than all the previous ones, you just increased the size of your structure. So std_variant should probably not be exposed through the API or ABI at all. Okay, we still have the automatic resource disposal. When the previous states get destroyed, all the resources they acquired just go away. And we don't have any boilerplate, okay? And we have no boilerplate regarding the definition of the variant. The problem is that it's just a little bit ugly to use with getif, but we'll come to it in a few slides. If you recall a couple of previously mentioned during a couple of recent years, there is std optional, which is a sum type of t or nothing, which is a special case of std variant just with a nicer syntax that just covers a single use case. We either have a value or we have nothing. And hopefully, in C++ 20, we'll get the std expected of, okay? We'll have std expected of te. If you want to listen more about expected, then I advise you to do so. There is a talk by Neil Douglas, or Neil, at 4 p.m. tomorrow. And this is one of the things where, unlike optional, which either contains a value or nothing, expected is meant to contain either a value or an error. So kind of like std future, and one of the reasons probably why Sean Parent doesn't think that std future is a monad, just a monad, it's because it doesn't really hold only a value, it can also contain an error, and the API is just horrible. So one of the really nice examples about of some types is the tennis kata. So the tennis kata is there are a lot of programming katas which are meant for you to improve your skills and then solve the same kata 10 times in a row in 10 years so that you can see how you evolved over the past decade. One of those is to implement the tennis scoring mechanism, because unlike normal sports, tennis doesn't have a proper scoring mechanism. It has something like, initially you would say that you have two players, and one player has one set of points and the other set of points. But if you say just int player 1 points, player 2 points, what will happen? You would be able to have 3-2-2, which is an invalid score for tennis. Okay? Do we have a normal mic? Hello? Okay, it works. So the next step is obviously to create an enum, because normal points didn't cut it. Let's create an enum that says love, which is 0 for some reason, 15, 30, and 40. And other names kind of make sense, but love definitely doesn't. And you would create 2 players, and now it's fine, right? The problem is that it's not, because for the most of the game, you have 15 love or 30, 15, but you can't have both players with 40 points. It's not 40-40, it's deuce. And after deuce, you don't have 50-40 or +1+ or something else. You have advantage this guy or advantage that guy. So this solution has a lot of less invalid states, but there still are some invalid states. So we could just get to completely separating everything as properly as some type should be. So we have 2 main stages, the numeric scoring and the deuce advantage section. The main scoring, the numeric scoring, is the 15, 30, and the deuce advantage, everything after that. But if we then continue splitting it in chunks, we have numeric scoring part from 0 to 30. Sorry, from love to 30. There are a couple of British people here, and they love tennis. Then we have a state where one of the players has 40 points, and the other guy has 0 to 30. As soon as the other guy reaches 40 points, it's the deuce, and then it's the advantage. And obviously, we have a finished state, which is when somebody actually wins. But that's the dull state, so we are going to skip it in this example. What would this look like? So we would create enum class points, which wouldn't contain 40, just love 15 and 30. And normal scoring would be both players have some of those points. The next state is 40 scoring. We have one player which has 40, and the other player who doesn't. So we just need to remember which player has 40 and how many points the other player has. After this one, switch to the advantage. We just need to store which player has the advantage, and for the deuce, we don't have to store anything. Okay, so far. And then tennis, without a single invalid state, is a variant of all of these states. Now you can try to make this break and, for example, for players to have 15 to 25, you can't. The code is really, really tight, so the type is completely, it doesn't have any extra states, it doesn't have any missing state, it exactly embodies the strange game that is tennis. The problem is that the more types you create in a variant, the harder it gets to actually process the data. Because if you just go everywhere with get if, it becomes a little bit boring. And sometimes you have different states which should have the same functions, like point for a player. All the states in tennis have the point for somebody. So you would probably want a nicer way to deal with std variant. One function that is in the standard is std visit. It accepts a function object or a function pointer or anything else, or any callable. And you can get and say, if you pass it a generic lambda, it will execute this exact lambda on any of the states, any of the possible states that is currently in the mState variable. So if you have similar APIs for all of the states, you would be able to do something like this. std visit will be really, really efficient. So it's not like dynamic dispatch or anything else. It exactly knows what is inside of a variant and directly calls the lambda, in this case, the generic lambda for the specific type. There is no type deduction, almost no type deduction at runtime. It's just internally one check of one integer without pointers or anything else. The problem is that while std visit is really useful with generic lambdas for writing out stuff to the cout, for debugging and stuff, sometimes you actually want to have different handlers for different types. And for that, you can go to the future and take the C++20 overloaded, or you can implement your own. What's the idea of overloaded is, instead of being able just to create generic lambdas, overloaded allows you to overload lambdas. So instead of having a single type, you can just say, okay, create a function object that is composed of this lambda for if it's called with this type, with this lambda if it's called with this type, and etc. How is it implemented in C++17? In C++14 is a little bit longer. In 17 is just the overloaded object inherits from all the lambdas you pass to it and just steals the call operator from all of them. The implementation in the slide is not complete. For this implementation, you also need the template argument deduction guideline, but it's one line apart from what's already written. And if you want to use the overloaded, then you can actually call stdvisit and say, for this case, if we are currently in the normal scoring, do this. If we are currently in 40 scoring, do that. Alternatively, you could have used the generic lambda and checked with const expiry if is the type of auto the same as blah, 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 but that's kind of ugly. So this is the most clean way that we can process std variants in C++ 17. One of the things that is being worked on by, I forgot the name of Bjarne's student, with Bjarne and somebody else, is Max7 pattern matching library. It's meant as an example of what pattern matching could do for potential inclusion into the core language later. But so far the library is quite ugly, but it's quite powerful. So instead of having what we had in the previous slide, overloaded of something, you can create different patterns and match what's currently stored in the mstate variable against different patterns. Now in this case, again, we just have a case where it's a normal scoring or we are matching against the types, which is not the only benefit that, well, it's not a benefit, it's almost the same as the previous code. The cool thing about the Max7 and general pattern matching is that you don't need only to match against the types, you can also match against the values. So you could implement the whole tennis game as a single pattern matching statement. For example, if we are currently in 40 scoring, and the first argument is the player who just got a new point. So if one of the players just had a 40 and he got a new point, he won, right? So you don't even care how many points the second player has, so just put an underscore. So if the current point goes to the first player and the first player had 40 points, it's the end of the game. Then the second case says, okay, if it wasn't the first case and we are still in the 40 scoring, this means that the point was won by the guy who doesn't have the 40 points. So if it's 30 points, we go to the deuce. So it means it was 40-30, so it's now deuce. Otherwise, we just need to increment the points for the second player. And instead of having all the if, else's, and everything else, you just have a single pattern matcher, which goes sequentially. Does this match? If yes, execute this. Does this match? If yes, execute this. And you can implement quite nice things with this. The only sad part about the Max7 is that it's a library-only solution. It's not a core language thing, so it's bound to be ugly. And the syntax, as you can see, is much uglier than anything that you would ever use. But let's hope that in C++ 23 or 26 or whenever we go to retirement, we'll get pattern matching in the core language itself. So this was about how to make your program state safer. Now we can move a little bit on to what was supposed to be the topic of this talk, and something that I promised in the previous year at Meeting C++. I was talking about how to implement your software systems without ever mutating any data, and I mentioned that one of the solutions are the immutable data structures. So the immutable data structures, the idea is that when you create, for example, a collection of integers, you can never change a single integer from that collection. You can just create a new collection that contains all of those and maybe a few more. So you can create essentially a modified copy, but you can never change the original. The idea why this is useful is that it allows you quite easy time-traveling debugging. Because if you just create new values, you can always scroll back to any of the previous ones. The second benefit is if you have multiple concurrent processes, and you give them a collection, if this concurrent process changes a collection, none of the others see the change. So you don't have any collisions or anything else, so no data races. Obviously, implementing systems in this way is not as trivial, so you have to design systems in a little bit more reactive way. And for that, I would refer you to my previous year's talk, because it took an hour, so I don't have the time to repeat everything again. This is just a continuation of how you would be able to implement a structure that works like an immutable structure. So all the previous values should be stored, never changed. You just create modified copies. Now, copying is usually a really, really expensive operation, so you can't really use std vector for this. If you wanted to use std vector and you want to create a modified copy, you would have to copy the whole vector and just change it in a few places, which is completely inefficient. One of the reasons why linked lists are really popular is that, unlike vectors, well, really popular in functional programming languages and nowhere else, is that they allow you to easily create efficient, copyable, modifiable structures. So we all know what a normal single linked list looks like in C. We would have just a node, and each node has a unique pointer to the child. And you would probably have some constant destructor so that you don't have the recursive destruction, blah, 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 blah. It's not really important. In functional programming, it's a little bit different, because all the lists that you create are always immutable. Creating a new list that has an element prepended to an old list is just creating a new node which points to the old list. Okay? So in this situation, we created L2, which is a pointer to E, and then E points to the body of the L1. Since we promised that L1 would never change, this means that L2 would never change as well. So we have high amount of data sharing between all the lists that we create. Because we are sharing the data, we can't use the unique pointer anymore. We need to use the shared pointer or something equivalent. If we want to create a new list which is just the tail of the previous one, again, we don't need to copy anything. We just need to create a new list which points to the, well, second element of the original one. And still, most of the data is shared, so you don't have actually the copies. There are no copies in the memory. You just have the differences. What happens if we want to append? Can we just append it like this slide tells us to? Of course not, because if you did it this way, this means we changed L1, L2, L3. We changed all the lists that shared this data because we appended to the end. Unfortunately, the lists, when I said they're popular in functional programming languages, I lied. They were popular a lot, but they still have all the same problems that they have in C++. So in this case, if you want to append, you will actually have to copy all the whole list. So the only operations that are efficient on immutable lists or persistent lists are prepending on the top and similar. If you want to insert somewhere in the middle, you would have to copy all the elements before the element that you inserted to. Okay, memory handling should be obvious. So the things that are efficient are head, tail, and prepending, and everything else for a linked list is O of n, which is definitely not efficient. So because this is really bad and functional programming languages rely on immutable data structures, it's obvious that they didn't stop at linked lists. A linked list is just the first example to show the data sharing idea, and then you can move to more advanced data structures, which are much, much more cool. One of the recently, let's say, discovered data structures, and the one that Juan Pedro implemented in the EMR library, is called a bitmapped vector tree or hash tree. Cool. It has at least 5 different names that I've seen in the literature. So whichever you search for, you should probably find the data structure. So I'm calling it a bitmapped vector tree, as it was the first article that I read, and they used the name. So what is the idea? The idea is that if you have just a small amount of items, you can put them in a vector. And for example, in the slides, I use the vector of length 4. Usually it's vector of length 32. So if you have one item, you have just a single bucket of 32 items, and just one is filled. If you want to add a new item, you just copy a bucket and append a new item. Is that okay for now? What's the complexity of copying a bucket length 32? It's a constant. So creating a new structure, so immutable old, we are creating new modified version. It's so far of n, which is cool. So we add a second item, we add a third item, and we fill the bucket. After we fill the bucket, we can create another bucket and put the items inside of the second bucket. But now we need to somehow collect all the buckets into one collection. We are going to create a new bucket as a tree. So we are going to create a bucket that points, the first item points to the first bucket, the second item points to the second bucket. And it should be fairly obvious how you would grow this structure further, right? So if you just continue adding items, when the second level gets filled, you just create another level on top of it. Now, there are several things that are really cool about this structure, is that just like with vector, index-based access is again of 1, unlike lists or anything else. So how can you access something in O of 1? The index is actually the key. If you chunk it into bit sections, in this case, since we are using buckets of size 4, we need to split the key into 2 by 2 bits. The last 2 bits are the index in the bottom level bucket, which is a direct access because we said buckets are vectors. The penultimate 2 bits are the index in the penultimate layer, and so on and so forth. So for each index that you get, you have the access for each of the layers, it's O of 1. Now the question is, I said that whole access is O of 1. Since most of the time you're using the buckets of size 32, the most levels that you can have in your program in C++ are 10 levels. So you will never have this tree structure larger, deeper than 10. And then you have O of 10 times 1. It's still a constant time. It's obviously slower than std vector, but it's still constant time, which is really, really amazing. That's the reason why I really like this structure. Now, memory access is O of 1, then all the buckets are kind of sized to match the CPU caches. So you have the data localization just like vector does. So you have that as well. But you have something that vector doesn't. So if we wanted to actually do the copying, we saw what appending an item looks like. But if you look at these three pictures, which of the data in the picture can be shared between all the three different collections? A, B, C, D, and well, for the last two, we can also share M and OP, and so we don't really need to copy all the data. If we want to append and create a new modified copy, we can just do something like this. The only nodes that you actually need to copy when changing something are the nodes on the path to the bucket that you want to change. So what's the complexity if you have std vector and you're creating a new std vector with one element appended? Linear. What's the complexity here? It's a constant. Again, it would be logarithm if we didn't have the limit for the depth of the tree. But as we said, the practical limit is always 10, so it's linear. And this is the place where this structure completely outperforms vector. You can create a lot of cheap copies without the linear performance. You have constant performance. Okay, we can switch this and this one. So what is the complexity of all the things? So getting the element by index, we already said O of 1. Appending is O of 1. Updating a value, again, we're just going to copy the path to the bucket that we need to change. So updating a value is also O of 1. Prepending is linear, just like with std vector. Concatenation is linear, just like with std vector. And inserting in the middle is linear, just like with std vector. Okay, so this has passed. There are optimizations or variations of this structure, which also allows you to do prepending in O of 1 and all of the other things in O of 1. So instead of, one of the possible ideas is not always to remember the first item to be the 0th, but also to have some kind of offset or something else. So each of the trees could have its own offset, and then you would still have all the same, but you would be able to do all the rest of the operations again in O of 1, which is quite neat. And if you want to see a couple of more functional data structures, there is a really, really good book. It was first his doctoral thesis by Chris Okasaki. And the doctoral thesis is available free for download, but he kind of completed it and made a proper book out of it, which is not available legally for free download. And tomorrow there will be talk from Pedro, Juan Pedro, at 5:45. Although he told me that when he saw that I'm going to talk about functional data structures, he kind of changed his talk. And at the same time, I saw that he's going to talk about functional data structures, so I decided to talk about std variant. So I'm not sure how if he will actually cover any of this tomorrow, but I strongly advise you to visit it because he told me that he is planning to talk about the architecture of the Elm programming language, which is immutable, reactive, blah, blah, blah programming language, and really cool thing to listen to. So you should probably first check out the presentation and then check out the purely functional data structures by Chris Okasaki. I mentioned that I'm writing a book, so you have a discount and blah, blah, blah. The book should be probably printed by the end of the year. It's officially not yet finished, but unofficially for you, it is. It's just being prepared for printing. And that's all. So, are there any questions? Okay. Okay, so he really likes std variant. Next. Okay, so the question was, again, that variant induces some runtime, slowness. And the problem with that is that sometimes you know in your head that what you're doing is correct and you don't need the safety that std variant gives you. If you are that convinced that you're not going to make bugs, then I agree, obviously, but in the same way, then Sean's talk is completely irrelevant, because if I know how to do this, I don't need to go to higher abstractions that Sean presented. The same thing was with Rhino's talk. We don't need the higher abstractions like futures or anything else, we have POSIX threads. So if you're really experienced and you're convinced that you can't make any errors, I agree. You don't need std variant, but most of the developers, even the senior ones, make smaller mistakes that haunt them for the rest of their lives.
I want a zero-cost std variant.
That's nice. So the second part was, you said, have I considered something that would work as std variant during the debugging, but not during runtime? The problem with that I see with that is that you don't get the error AI. You need std variant to free the stuff from the previous state. That's one of the main reasons why I really adore std variant. It has ugly API and ugly everything, but the fact that it kind of constrains your resources is a really good one. And before we move on to the next questions, I have vouchers for people who ask me questions. So it's for the ebook version, and yeah. Okay, next question.
Is this microphone working? Yeah. So you say that these BVTs are constant time because they have a cap on the depth. Is the same not true of any tree-shaped data structure?
Nope. So most of the, depending on the tree. So you have the tall trees and you have the wide trees. For the wide trees, yes, it's true, and this is one of the wide trees. But it's not, there are a lot of data structures which are just binary trees, or they don't really spread all that much.
So you're saying that because you have a 4 tree instead of a binary tree, basically?
It's not a 4 tree, it's a 4 tree just in the slides.
Oh, it's 32.
In practice, it's 32, and all the memory space that you have on a 64-bit computer would fit into a 10-level tree.
Okay, maybe I should get to my real question, which is, even though you're capped at 10 levels, you still have a lot of pointer chasing to get to the bottom. I mean, you chase 10 pointers.
Yep.
Is there an advantage over a finger tree where you have the ends at depth 1?
There are optimizations for this that also keep some things at the root level, so that you optimize the appending and everything else. But as I said, Juan Pedro is probably better person to talk, because the implementation that he did is really freaking amazing. So okay, 5 minutes more. I benchmarked it against std vector, and it was just barely slower. And you should probably ask him how he actually managed to do it.
Thank you very much.
Right, when you talked about std variant and std visit, you showed us that later it will be possible to just write different lambdas that already have the specific type in their function prototype, couldn't you just already write freestanding functions that are function overloaded to the specific types of the variant?
And use it with std visit, yeah. But this is prettier, and this is more awesome, you know, because if I just use the freestanding function, you would all be like, who the is this guy, and what is he talking about? And then I show something really cool, which is called overloaded with brackets and lambdas inside, and it looks really smart, right?
Sure.
So in essence,
work at this point yet.
yeah, the difference between a freestanding function and a lambda, just like in any other part of your program. If you just need it for one time, then you really don't want to declare it as a freestanding. And that's why lambdas in this case are quite useful.
Okay.
Okay. And I have two more left.
One more question.
Okay.
In the case of the tree data structure you show there, if you make several copies of it, you will have to have a shared ownership scenario between all the tree nodes. And if you use it in a multi-threaded environment, it has to be atomically counted shared values if you don't have a garbage
yes,
collector.
allocation, and when you create a new instance or increasing the reference count in the shared pointer, obviously, you have locks. But that's not something that you should implement. It's already in the shared pointer.
So it's typically not expensive to do. It can be.
It is expensive in the terms of std vector, but it's really inexpensive when you consider all the benefits that you get if you need the benefits. If you want free copying, then std vector is not a solution. Okay?
All right. Thank you so much.
Any more questions?
Not really a question, just a...
Where are you?
Here? I'm here.
I have no
Here, back here.
Oh, okay.
Not really a question, just a clarification. Isn't the BVT that you presented pretty much B trees that we have been using in databases for a couple of decades?
They're similar. All the trees are similar. So this is some... as I said, this thing has 5 different names. One of the reasons why it's called a tree and not a TREE is that because trees are the prefix structures, and in this place the key is the prefix structures. With the trees in databases, you don't really have they're not really optimized for this. They're more optimized for let's say range access than identifier access, index access. But they are similar. The difference, the database trees and red-black trees and everything else can also be optimized in the same way, so you can create immutable data structures out of them. But this has a couple of small things that makes it really, really awesome.
Thanks, I just wanted to point it out.
Okay, do you want a voucher?
Why not?
Yeah. Okay, so no more vouchers and the session is over. So thank you all for coming.